So now that we've talked about the ForkJoinPool class, let's take a look at the ForkJoinTask class. And you can see here from this introductory diagram that ForkJoinPool will have a bunch of ForkJoinTasks that run inside of it. And ForkJoinTask, in turn, is a superclass that is customized by various subclasses like recursive task and recursive action and so on. And we'll cover those subclasses in the next part of this lesson. So what is a ForkJoinTask? Well, a ForkJoinTask is a class that associates a chunk of data, which is really a subset of the overall data, along with a computation that can be performed on that data. And the purpose behind doing it this way is to enable so-called fine-grained data parallelism. So one way to think about this is a ForkJoinTask is sort of a lightweight Java thread. If you think about Java thread that we talked about when we covered the details of threads, remember it had a runtime stack. Java thread has its own registers. It had its own thread local storage. It has a whole bunch of other things, and there's many layers involved that reach down into the operating system kernel and so on. And while that makes it very powerful and makes it possible to schedule it and manage it by the underlying operating system scheduler on different hardware cores, it also adds a lot of weight to a thread. In contrast, a ForkJoinTask is much more meager and much leaner. It doesn't have its own stack. It doesn't have its own registers. It doesn't have its own thread local storage, unless you program thread local storage for it, but you typically wouldn't do that. So one of the consequences is you can have a very, very large number of ForkJoinTasks that are then run or multiplexed atop a much smaller number of worker threads that are managed in a thread pool by the ForkJoinPool. So you can see here we have a pool of worker threads with some number of threads, and then we've got a whole boatload of ForkJoinTasks that are multiplexed or run on top of the threads in the pool of worker threads. And again, each worker thread has all the state that's needed to run on the underlying processor cores, but the ForkJoinTasks do not need that. There are two primary methods that are important in a ForkJoinTask. And as you might expect, they are fork and join. And they're responsible for handling parallel processing and splitting of things up into subchunks or subtasks, and then merging those subresults coming back from those subtasks back into results. So the fork method arranges to asynchronously execute this task in the appropriate pool, in the ForkJoinPool that it's associated with. So the key point there is arranges. It doesn't start to run it right away, but it arranges to get it run. And you can think of fork as basically a lightweight variant of thread start that creates a child ForkJoinTask and then arranges to have it run. And we'll talk more about what arranges means here momentarily. What it means here, of course, is that fork doesn't run the task immediately, but it places it on a work queue in the calling worker thread. And this work queue is organized as a deck, which stands for double-ended queue. And we'll talk quite a bit more about decks and how the ForkJoinPool worker threads use these decks. Each worker thread has one deck, and it uses that to essentially queue up its work. Join, which is the other half of ForkJoin, returns the result of a child task to the parent thread, or parent task rather, that forked it. So when something is forked, then you get back a ForkJoinTask, and then you can later join with that task to return the result of the computation when it is complete. Now, this is also quite interesting. If we think about fork as being kind of a lightweight thread start, you can think of ForkJoinTask join as being something like a lightweight thread join. However, unlike thread join, which actually blocks the calling thread till the computation is done, ForkJoinTask doesn't just block the calling task. Instead, what it does is it uses the worker thread that called it in order to run other tasks, or more specifically subtasks, in order to move things along. And I like to refer to this as the collaborative Jiffy Lube model of processing. And here's kind of the metaphor for this. If you've ever taking your car to get the oil changed at a place like Jiffy Lube, which is an oil changing place, they typically have multiple bays. And what you do is you get out of your car, someone drives your car into the bay, and then a group of workers go ahead and change your oil. And they also do other things, like they might check your air pressure on your tires, check your air filter, look at your fluids, like your windshield wiper fluid, in addition to changing your oil, and just do other sort of routine maintenance things on your car. And the way it might work is there might be, let's say 2 workers per bay. And if all the cars are pulled into all the bays, then each worker team will work on the car that's in their bay. However, if it turns out that there's maybe only 1 or 2 cars in a multi-bay Jiffy Lube garage, then you can imagine a scenario where those workers would come from their bays and go over and pitch in order to increase the rate at which they're completing the work on the cars that are there. So that's the pitching in concept in a collaborative model of processing. So the point here is, if you're joining with something, you actually don't just block, but you pitch in and do some processing in order to leverage your core to make more work get done per unit time. When a worker thread encounters a join call, it will process other subtasks or tasks until it notices whoever called the join call is done, in which case it can then return that control back to the caller because it's got its result. Now, ForkJoinPool, which is the kind of the interface class we just talked about, enables non-ForkJoinTask clients to process ForkJoin tasks. And the way it does that is it defines 3 publicly facing API methods, execute, invoke, and submit, that allow non-ForkJoin task clients, like just regular good old code, that's Java code, to hand ForkJoin task or an initial ForkJoin task off to the ForkJoinPool to be executed in the context of the pool. And we'll come back and talk about these 3 methods, execute, invoke, and submit, later. And you'll get a chance to play around with some of these methods when you do your programming assignment. So what happens here is when a non-ForkJoin task client inserts a new ForkJoin task into the ForkJoinPool by calling execute or invoke or submit, what happens is it takes that task, and as you can see here, the non-ForkJoin task clients call those methods or call a method, and that sticks the task into a shared queue. And that shared queue is shared by all the worker threads in the ForkJoinPool. And those worker threads will look periodically at that queue, and if they see something in the queue, they will take the stuff from the queue and then start to do the processing. And once the ForkJoin task is in the ForkJoinPool, then all the cool magic happens. And we'll talk a lot more about what that magic involves. And as you can see with the link at the bottom of the slide here, the key thing that happens in a ForkJoinPool that's quite different from other types of thread pools in the Java Executive Framework is the concept of work stealing. And we'll talk about what work stealing is too. The goal of work stealing is to maximize processor core utilization. And again, think back to the collaborative Jiffy Lube model that I was talking about before. If you can imagine a Jiffy Lube center, the goal is to get the cars through the Jiffy Lube center as quickly as possible, thereby increasing revenue, because if you can get more cars through per unit time, then you can make more money because more people can get their oil changed and they won't be sitting around waiting as long. And so the same thing is true with work stealing. The idea is to keep all the worker threads in the ForkJoinPool, which of course map to the underlying processor cores, just as busy as you possibly can so that you get more work done per unit time. In other words, you maximally enhance or maximally leverage the amount of processor core utilization. So these are, again, some of the key concepts that are related to the ForkJoin framework, looked at from the context of the ForkJoin task. We will, of course, go through the methods in the ForkJoin task in a lot more detail shortly too, but I'm still just trying to give you the big picture view of what's going on with this very powerful, but a bit overwhelming framework when you're exposed to it at first.